Okay, on to page number 4, I believe. So first number, question 12. For the analog signal given by this formula, A, what is the minimum sampling rate that could be used in analog to digital conversion such that a receiver could accurately reconstruct the signal? So the sampling rate we need to use is Nyquist, which must be greater than 2 times Fmax. So in this case, the Nyquist sampling rate is the one that will not cause aliasing. So we want to make sure that we use at least that minimum frequency of 2f max. So 2 times f max we're going to take from our equations here. So keeping in mind that first number is the amplitude. The second number is the frequency. So we have 400, 600, and 1100. So our max is 1100, which means that we need to be greater than 2200 hertz. So that's our Nyquist sampling rate. And then the next part, if we used a sample rate of 3000 samples per second, would aliasing occur? No, because it is greater than the Nyquist rate that we calculated in the previous problem. Okay, so this is just a follow-up to that to check your understanding of the Nyquist sampling rate. For part C, if we used a sample rate of 6000 samples per second in analog to digital conversion along with a 5-bit quantizer, what would be the resulting bit rate? So bit rate, RB, is in bits per second. So we have 6,000 samples per second. And if we multiply that by 5 bits per sample, we're going to cross out these two terms, the samples, and that's going to give us bits per second remaining. And that is going to be 30,000 BPS, or if you want to be clever, that is 30 kbps. I'm fine with either. And then part D, if the signal was quantized by a 5-bit quantizer and the resolution was 1 volt, what would this imply as the minimum and maximum voltage found in the analog signal? Okay, so this is using the equation Q for the quantizer resolution. Q is equal to Vmax minus Vmin over 2 to the n, where n is the number of bits. So we have that Q is given to be 1 volt. So 1 volt equals Vmax minus Vmin, and we're given that n is 5. It's a 5-bit quantizer, so 2 to the 5, which means that 2 to the 5 is 32. So 32 equals Vmax minus Vmin. Keep in mind that we're using a sine. This is for a sine curve. So whatever Vmax is, it's going to be the opposite of Vmin is just going to be the same value but negative. So if Vmax is up here somewhere, Vmin is going to be the same negative value. That means we're looking for basically 32 divided by 2. So Vmax equals 16 volts. Vmin equals negative 16 volts. And if we plug those into that equation, that'll give us the value of 32 volts. So this is just basically, not trial and error, but understanding that Vmax and Vmin are going to be the same number, just Vmax is absolute value of Vmin. Okay. Question 13. Which actions below will reduce the effects of quantization error? Use AM instead of FM? Nope. That's just how we're sending the signal over an analog channel. So that's nothing to do with digital conversion. Use less bits per sample in your AD converter. Nope, that will increase the quantization error. Increase the size of the quantization intervals. That won't really have an effect in terms of the quantization error. It'll just, decrease the sampling rate. Use a higher sample frequency. Nope, that's also not related to the quantization error because it's sampling. Use more bits in your AD converter, and that's the one. So that will reduce the effects of quantization error if we use more bits. Question 14. Which digital modulation techniques are combined in quadrature amplitude modulation? So QAM. QAM is usually represented as some constellation like this where we have multiple amplitudes and multiple phases. So that is the answer here, which is phase plus amplitude. This is mostly just a definition question. Know the definitions of these different types of digital modulation. Okay, in question 15, in the space below, provide a sketch of a constellation diagram for each of the following types of digital modulation. So there are quite a few here. I will do all of them just to be helpful, hopefully. So BPSK is binary phase shift keying. That means that we are using two different angles, meaning that if we draw our constellation, we have angles at 0 degrees, 90 degrees, 180 degrees, and 270 or negative 90 degrees. Either is fine. So we'd probably use an angle at 0 degrees and an angle at 180 degrees. If we want to label these, we can say that it's 0 and 1 because we have two possible values to use there. So it's just 1 bit in this case. B, QPSK. So this is quad phase shift keying. That means that we have 4 angles instead of just 2 angles like we had in BPSK. So we can do either this, and this, keeping in mind same amplitude for all of these, they're on the same circle, or we could do the intercardinal points as well. Either one is fine. And we want to label, as usual, the degrees and the bit patterns that we have at each of these. So in this case, if we have 4 symbols, our equation n for the number of bits is log 2 of m, where m is the number of symbols. So if we have 4 symbols, then n is going to be 2. So we label each of these with a 2-bit pattern. So 0, 1, 2, 3 in binary. Part C, 8 PSK. So 8 PSK meaning 8 different phases. So we still want a single circle. We don't want to use different amplitudes yet. And since we need 8 different phases, we can draw any 8 angles and it's fine. But generally we're going to use the ones that are more separated. So we're going to choose the cardinals and the intercardinal points. So again, drawing the angles for each of these, and we can label our points. In this case, n is log 2 of 8, so that's n is going to be 3, so we need 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So all of our different 3-bit patterns. Part D, this one says 8 QAM. So QAM meaning quadrature amplitude modulation, so phase and amplitude. We're using 2 different amplitudes and 4 different phases. So we need 2 circles because it's 2 different amplitudes, and we can choose any 4 different phases, though they should match between the 2 circles. So I'm going to do the different one from what the solution gave and say that we're going to do the cardinal points. So north, south, east, and west. And the solution, I think, online gives you the intercardinal points, so you can see that as an example as well. And then we're going to label these. We have 8 QAM, so 2 different phases, or 2 different amplitudes, 4 different phases. That means we have 8 symbols. So log 2 of 8 is 3 again. That means we can label each of these with a 3-bit pattern, and this is sort of up to your discretion, however you want to label them. I found this was easy because then at least the last 2 bits are always the same for each of these, and we can just label each point to say what it is. And again, you should label your angles so that we know which direction you're trying to point in. And finally, part E, 16 QAM, that uses 4 amplitudes and 4 phases. So this one's going to be a little bit more difficult to draw, but 4 circles, so that we can have 4 different amplitudes and 4 different phases. So again, I'm going to give a different solution than the solution guide, but we're going to draw out all of these dots. And also, because I don't quite have enough space here, I'm not going to draw out all of the bit patterns, but it would be starting from 0, 0, 0, 0 all the way up to 1, 1, 1, 1. And again, we should have our angles so that we know exactly what this diagram is showing. Okay, we could label each of these points with some number between 0 and 1, 1, 1, 1 with 4 bits for each thing. And that's again because 16 QAM means M is 16, N is then going to be 4. Okay, that's it for this page.